all the things. So when we take our break, we'll take our 10-minute break again, probably close to 3:30. Once that's done, I'm going to make the quiz go live, and you guys will have 20 minutes to complete it. And then we'll come back from the quiz and do a little bit more lecturing. But my goal for today is for us to be done right around the 4:15, 4:30 mark, covering central tendency, because it's a topic that most of you are going to be familiar with. And so that quiz is going to be specifically on that. Any questions?
I have a question.
Yeah.
So was the lab due today before class? Because it says online it's due tomorrow.
Oh, it's anytime. So I think I made it due for 12:01, so that's technically tomorrow. By the end of today, if you need tomorrow, that's totally fine. You will quickly find I'm not a professor who is losing a lot of sleep over deadlines and time. Just let me know if you need a little extra time, we'll make it work.
Okay, thank you.
And Olympia, I am curious though, when you say you saw online that it was due tomorrow, do you mean by the syllabus or somehow on Course Connect?
I think I saw on Course Connect.
Okay. And I have no control over the due dates that get assigned by that, so sorry about that. Okay. Quick question. Was everyone able to access the lecture from last week, the recording of it?
Yep.
Okay, so from now on, what I'm going to do is I'm going to upload them directly to YouTube, to that channel, and you guys can access it anytime, but I'm not going to copy a new link in that week. So what I did is I added it, and in fact, maybe I could just show it to you real fast. Here, if I can do this instead. Do you guys see Course Connect real quick? I clicked, so this is the class lectures. It'll have the link to the YouTube page that you guys can watch at any time. Sound like a plan?
So the quiz today is over what we learned.
What we're going to learn today.
Okay.
Yep, what we're going to learn today with central tendency. Yep, good question. Okay, so let's close that and make this go here, open that. I want to make sure again that you guys can see it. Slideshow from beginning. Whoops, that won't work. Here we are. And bigger and share screen. All the steps, you guys. And I'm verbalizing every single one of them just for ease. All right, can everyone see measures of central tendency?
Yep.
Okay. All right. So when you hear that, measures of central tendency, what comes to mind?
Average.
Average, right? So central tendency meaning the middle, right? That's most often what people think of. So we are going to be looking at different ways to measure the middle, or where the bulk of people find themselves, which is average, and it's the middle. All right. So here's what we're going to do today when we talk about this particular chapter. We're going to talk about the importance as to why we measure central tendency. Why do we care about that? We're going to be able to learn how to calculate and interpret the mode, median, and mean. Those three things are in fact different, and we'll talk about what they are and how they're different, and in what case you'd want to use one versus another. We're going to talk about each of their strengths and weaknesses, especially as relative to one another, because again, you need to select which one you want to do. And we're going to talk about the shape of the distribution that they come from. This is going to be especially important for the second part of the class. We'll talk about z-scores and why we calculate that. Now, let's temperature check here. How many of you guys have heard about some of these terms that I've used? Mode, median, mean. Is that familiar to people?
Yeah. Yes. Yeah.
Okay. How about a shape of a distribution?
Like the standard deviation ones, like the bell and the...
Yeah, so actually spot on. Bell curve. Yep. Standard deviation is a little bit, that's a measure of variance. We'll talk about that probably next week. But a bell curve, totally. So somewhat familiar?
Yeah.
Okay, super. All right. So what is a measure of central tendency? It's the numbers that describe what is average or typical for a distribution. So again, what if I'm interested in seeing how often or how likely or how frequently does one get into a car crash between ages of 18 and 25, let's say, if I'm looking at that. There is going to be some people that's going to be a 0, right? And then we're going to start looking at a frequency table, right? A few people will have 1 accident, maybe a lot of people will have 2, and hopefully very few have had 3 or more, right? So it'll do kind of this bell curve. In fact, this is what it would look like. Hopefully all of you guys are familiar with a bell curve. Now I need to have my, oopsie. You guys probably can't see that. Oh, there it is. Can you guys see that?
Yep.
Okay, bell curve. So at either end of these are called the tails. At either end, very few frequencies, right? It does not happen a lot. And then the middle, that's when you see the most frequent occasions. So another good example would be, I gave out a test, what were my students' scores, right? Well, a quote unquote good test that discerns between the A students and those who've never been in the class would be that a small number would get A's and an increasing number would get B's. The bulk would be kind of in that C range. A few others would be at the D, and again, very few at the tail would be an F. So this is considered a normal curve or a bell curve. Okay? That's how that shakes up. So again, it's where is the middle of the distribution. It's the central value. The idea of central tendency is also kind of thought of as the most common score, because again, you're talking about frequency, and we talked about frequencies last week, right? So you're counting and you're figuring out, again, what is the most common score. It's especially useful when we're looking at several different variables and looking at different frequency distributions. When you're trying to compare different factors and comparing them to one another, having really an idea of what does that middle ground look like is very important. And more specifically, when we look at z-scores, it's standardizing a central tendency so that we are all on the same page and we're comparing apples to apples. So again, in some disciplines, frequency tables are very rarely shared. So for instance, if I was asking, 1,000 people in my study for their age, it would be very unlikely to get a frequency table, like how many people were 18, how many people were 19, or even grouping them, how many people would be 18 to 25 or 26 to 31. It's more common to do an average or a mean. And so I would say your average participant is 37 years old, let's say, right? So that would be another way to look at that. Okay, so mode. That's the first one we're going to talk about. The mode is the category or score with the largest frequency in this distribution. So if you looked at a distribution with 10 numbers, whatever the number is that occurred the most often, that would be your mode. It can be calculated for all levels of variables, nominal, ordinal, and interval ratio. And it is the common measure of central tendency for nominal variables. So for instance, if I asked a large group which religion has the most number of people, and I asked them, what religion do you affiliate with? Whatever one came up most frequently, right, had the highest frequency, would be the mode. Mode is rarely used for numerical or quantitative variables because it's often not as representative. So let's do a quick exercise. I'm trying to see how I can make this work. So you guys will just need to speak up. So I'm going to ask about number of children that you have in your family. So when you think about yourselves, how many siblings do you have, ranging from 0, I'm assuming, to high? So if I could get a yes, or even just say your name, if you're an only child.
Yes.
Okay. It looks like just one. All right. How many of you have only, one sibling?
Yes.
So that means there's 2 kids in the family. There's only one person?
Mm-hmm.
Kyle? 2? Is that 3?
Kyle and Haley.
Kyle and Haley, that's what I was hearing, only 2. Okay. How many of you have 3 kids in your family?
Yes.
Me.
Yes.
Yes.
Okay, I think I heard 6 there. How about 4 kids in your family?
Yes.
Yeah.
Yes. Yes.
Okay, I think I heard 5. How about 5? 5 kids. Okay. How about more than 5? Okay, well, that is not adding up, but I probably misunderstood some of the yeses. So it looks like for 1 child, we had 1 participant or 1 person. 2, we had 2. 3, we had 6. 4, we had 5, and that was the highest. So if I looked at this, again, don't mind the doodling, what would be my mode?
3.
3 would be my mode. Why is it 3?
It's the most frequent out of the bunch.
It is the most frequent of the bunch, okay? So I'm going to keep this example, and we're going to calculate the median and mean as well. So for this, we would say the mode, the most frequently occurring number of siblings is 3. Now, offhand, does anybody know what the national average is of average number of kids per families?
I think it's 3.
Oh, it broke up a little bit there, Bree. What were you saying?
I think it's 3.
You think 3?
Isn't it like a weird decimal, like 2.3 or something like that?
Yeah, it is a weird decimal. Yeah, it's definitely a decimal because again, they average the numbers, right? So then you're not going to have a whole number, which that's a pitfall too, right?
5 kids.
2.5. Okay, so based on that, what hypothesis might we make that our mode is 3? If we know that the national average is 2.5. No wrong answer here. Just kind of curious what you guys can think.
Well, we could look at age gap because this is currently. I mean, we could look at how old our parents were, and then
Okay.
the time of when we were born. kind of.
Okay. Yeah. So looking at the values, if the mode of our class is most people have 3, they're part of a family that has 3 kids, and the national average is 2.5, our class would be considered above, at, or below average.
Slightly above average.
Slightly above average, right? And so what might be a reason, again, thinking out loud, why we might be above average?
A smaller data set.
Smaller data set. Totally, that's a good point. So this is more susceptible to like idiosyncratic reasoning rather than generalized comments. Sure.
We all come from the same area, so if we're talking like geographically,
Right. So maybe there's something geographic, like people in the Midwest have more kids than on average. We could say, hey, we're a Christian institution, and maybe Christian families or Catholic families have more kids than the average, right? So we can start, so having that data, that single measure of central tendency opens up the door to a lot of hypothesis testing, right? Why is it this way and not another, right? What could explain away the difference? So I want you guys to start thinking that way, especially when you're coming up with the labs, you'll get different values. Start thinking about those hypotheses, just like you did last week. Like, what might be a reason that would explain away the data that I gathered? Doesn't have to be right. Again, this is not a full study where we're going to be, refuted or shown that no, it's something else, right? It's just some hypotheses. Okay, so let's look at this, for instance. So this is the affiliated or one's identified religion in the United States, according to this poll that was taken in 2016. So this is given in terms of percentage of the US population, and it shows here the different religious group that one identified as. So looking at this table, what would be the mode?
Christians.
Christians, right? Is that clear to everyone? Hopefully, yes. Okay. It's the most frequently occurring number, or said in percentages, the largest percentage of the group identifies as Christian. Okay? Now, it can also be, since the mode is the high point in a distribution, or the most frequently occurring number, when you look at a histogram, for instance, it can be your highest point as well. So in this, we can see that the highest point is 8. That's the one that is most frequently occurring. Just eyeballing it, we'd be able to see that. Now, you guys know, we'll talk about in a second, doing averages. Averages require calculations. This, you can just eyeball it. You say mode is 8. Okay, so looking at this, take a piece of paper, count it out, create a little frequency, and tell me what is the mode. Once you have it, say got it, so we know, and then I'll have everybody share.
Aquinas.
Aquinas.
Okay, how did we determine that?
Tallying them up and then finding the most frequent.
Okay, so what was the number for Aquinas?
8.
How about Calvin?
6.
And West Michigan?
4.
Okay. Ferris?
2.
2. Okay. So based on that, we got the frequency of each, and we were able to determine which one was the most frequently occurring. Now, would you be able to get a mean from that, from this data? Or an average? If someone said, like, what's the average university people go to?
Just from this data set? No.
No. And why is that? What is it about this data that would not allow us to give a mean or an average?
Well, there's not really any numbers and it doesn't actually mean anything. It's just a bunch of names.
Exactly.
Right now.
You're absolutely right. So this is only nominal data, meaning there's no numbers attached to it. So we cannot come up with an average, right? We can talk about the frequency and that frequency distribution, but that's about it. We can't do much more than that. So that's why a mode is especially helpful when we're doing that kind of illustration and trying to talk about central tendency with nominal values. If you have actual like figures and a measurement, then it may make more sense to talk about the mean or the median rather than the mode. But especially with nominal data, that's the most helpful. Okay. So you could do the same thing. What's the most common foreign language spoken in the US? You would ask people, tally up the frequency and figure out what is the highest frequency in terms of spoken language. That'd be another way to calculate it. Again, that's for nominal data. Okay, and you can see here the number of speakers for each of those, and you see there's Spanish right here at the top, all the way down to French Creole, that's a smaller number. And so the mode is Spanish because it has the highest number of speakers. Okay, now let's talk about the median. That's a little bit different. Now, the median is a score that divides a distribution into 2 equal parts so that half of the cases are above that median point and half of the cases are below. So the middle score, or it's the average of middle scores in a distribution. So this is especially important. If you have a data set that has an odd number of instances, you can find actual, like, here's the middle score, because you can organize them. We'll do that in a second. You organize your data, find the midpoint. But if it's an even number, then you're going to have 2 numbers. So you're going to need to do the average of those 2 middle scores in the distribution. So for instance, the median weekly salary of full-time US workers in 2015 was $825, which meant if I took everybody, right, all US workers, and looked at their salary, if they're working full-time, and I organized the data from the lowest amount to the highest amount, 825 would be right smack in the middle, which means half the workers made more and half the workers made less. It can be calculated for ordinal or interval ratio data. It cannot be calculated for nominal data because, as Ashley mentioned earlier, there's no value attached to it, right? It wouldn't make sense to organize it or order it in a certain way because it's just an abstract, you know, non-numbered variable. Okay, so again, the value at which half of the ordered scores fall above and half of the scores fall below. So if I look at 1 through 5, right, this is an odd numbered data set because there's 5 values. Finding the midpoint, it's very simple. I just go right here and here's 3. So I know that half is above, 4 and 5, and half is below, 1 and 2. So the median is 3. If I look at the same thing and I just take away 5, 1, 2, 3, 4, now I don't have an exact midpoint. So I need to take the average of my 2 middle spots. The way I would do that is I would do 2 plus 3, that equals 5, divided by 2 equals 2.5. So the median for that is 2.5. Does that make sense to everyone, how we go about doing that? Pretty clear? Okay. Okay. The key here is that whatever data set you're working with, you are going to need to organize it from smallest to largest. With a data set, oftentimes it'll all be mixed up. So organizing it is step 1. Then finding the midpoint is step 2. Okay. So here's an example. This is the number of hate crimes reported in the 9 most populous US states in 2014. Okay, so here are the states and the number of hate crimes. There's 9 states that are being observed or calculated, so that's why N, that's my sample. My sample size is 9. So first you would arrange the number of hate crimes in order from the lowest to highest, okay? So what is the lowest number here?
50.
50. So then I would go up, right? From 50, go to 65, then go to 140, then go to 145, I missed 109. 109, 140, 145, 311, 336, 545, 759. Okay, I've now ordered them in ascending order. Next, you would need to figure out what is the exact midpoint. And the way I would do that is you do 9, so again, you're doing the tallying, you're trying to figure out what is your exact midpoint. And in this case, because there are 9 stated numbers, finding the midpoint is right in between, it's an odd number, so it'd be number 5. So the median, once I've organized it all, right, we had said that's number 1, 2, 3, 4, this is number 5. So 145 exactly divides the distribution in half, so that half is below, half is above. Does that make sense? Yes.
Could you go over, so the median, could you go over that one more time, how you, 145?
Sure. So what I do first is I have to organize the data from the smallest reported value to the highest, okay? And then the easiest way is either like right here, it would be to add number 1, right? Like, I can't really,
50, 65.
right, so 50 is in the number 1 spot, 65 is number 2, 109 is number 3,
Oh, so we're
140 is number 4,
got it.
140 is number 5, right? 311 is number 6, 336 number 7, all the way up to 759, which would be number 9. And then I go back and I'm like, which one is my midpoint? And because I have 9 data points, the midpoint, it's an odd number, the midpoint is right there in the middle at case number 5, because there's 4 below and there's 4 above.
Got it. I forgot we had to organize it first.
Yep, no, it's a common mistake. Any other questions about that? Okay, let's see if we can do a few more. So this is, again, describing the same thing. Now, the number of hate crimes reported in the 8 most populous states. So again, we're looking at the exact same values, except we've just deleted one of them, just for the sake of example, so we can see what that looks like. So we deleted 50 with this one. So what do we do if it's an even sample size? It's an even numbered sample size. Well, now we need to look at the average between the two that are in the middle, right? And the way I would do that is I would add them up, 311 plus 145 divided by 2, which would be 228. So the way I would report that data would be the average number of hate crimes reported in the 8 most populous states is 228. Does that make sense?
Yep.
Okay. Whenever it's an even data set, that just requires a little bit more math in terms of, whoops, I didn't mean to do that, in terms of finding out your exact average. But it's not meant to be complicated. Again, you're just doing the average between those two values. So it's going to be adding them and dividing them by 2. Okay. Let's look at this. This is now the value, the median frequency distribution, specifically with people's political views. So these are the different political views that are possible, right? This is our total N 1442. You can see here how frequently it occurs. That's same again with their percentages. And you would want to find the median. What is, again, the most occurring number? So we would be taking this right here, our total N. We always add +1 for making an even divide. So it'd be the 721.5 case. That's where we're trying to line it up. That's the case number where we want it to be. So that's how we would calculate it. This one's a little bit more abstract to think of, but there's a whole description of it in your textbook as well. Again, it's the same idea. You're looking at an entire data set and you're finding that midpoint so that exactly half is below and half is above that point of view. Okay. Percentiles. This falls in a similar pattern. Now, when do we hear about percentiles? What does that connect for you guys?
I think education, when it's like, oh, you're in the 94th percentile or 86th, it's like ranking.
Ranking. And you're thinking in terms of scores or class standing?
Yeah.
Okay. What's another thing that we think of?
Fetus
Like-
growth.
Distribution shape.
Okay, I heard 2 things. Something growth?
Fetus growth.
Fetus growth. Okay, so when a fetus is in utero, what percentile are they in? At what rate are they growing? And Bree, what did you say?
Oh, I just was thinking about like the distribution shape when they have like the 3-point set, or I don't know how it goes, but yeah.
Yeah,
that's the thing.
you definitely have percentiles in a distribution. Absolutely. I have kiddos, so I often think about that. You go to the pediatrician every year and they're like, oh, based on his height, he's in the 85th percentile. The idea of percentiles is organizing data in a specific distribution so that you are looking at a percentage. So if you were to line up all of the occurrences, right, all the data, starting at the smallest to the highest, it's finding where they fall and converting that to percentages. So, for example, a 75th percentile is a score that divides a distribution so that 75% of the cases are below it, and there's only 25% that's above. So as soon as you hear 75th percentile, you know that's kind of above average in some way. You can also talk about it in terms of quartile. Quartile is another word. It's just dividing a distribution into quarters, so 4 segments. So you can have second quartile, third quartile, upper quartile. That's the language we use around that. So that's another way, again, of organizing our data based around a central tendency. Okay, so here's an example to follow that up with. That's the days of the week where having dinner with their parents, again, this is the weird example, but how many times do people have dinner with their parents? So this is the total frequency, and we can look at the percentages. So those who have dinner with their parents less than 1 day a week, we're at 1,400. For instance, 6 to 7 days per week, 3,300. So that's how we would write it in, right? So that's how the data fell. And finding out what's the median, how would we know what the median is?
Add 1 to 8,907, then divide by 2, and then whatever case that is, that would be your median.
That's exactly right. So we would do exactly what Kyle just described. So we would take our total n, which is right here, add 1 to it, divide it by 2, and we would know our middle point, which would be something like 4,700-ish. Someone could do the math on that. And we would find that case number to figure out exactly where we lie, and that would be the median. Okay?
Always divided by 2.
Yes.
Okay.
Yes, you do that. I mean, if you're looking at a data set that has 5 points, you don't need to do 5 plus 1 divided by 2. You kind of know it's 3. But most often it's going to be super large data sets, so it's more helpful to do it that way.
Okay.
Yeah. And now what is the percentile? So if I look here, this is the cumulative percentage, right? So this is 16% less than 1 day, and then it's 6% for 1 day. So cumulative, you're adding those together, it's a 22. So which category is at the 50th percentile or below? What do we think?
Is it the 3 days per week?
Yep, so it would actually include part of this 4 to 5 days per week, right? Because 41 total percent, there's still 9 that's into this section. So this is kind of a funky one where you probably would say it's a 3 days a week or less is probably less than 50th percentile, and above 50th percentile would be 4 to 5 days or more with their families. Again, this is your book likes to use funky examples, but that's how we would do that. Okay, so all of those are important. Mode, percentile, median. Another one that median's often used for is the median income. I'm sure you guys have heard that in the news. Median income. We don't talk about mean income, we talk about median income. And we'll talk in a minute as to why we do it that way. But the most common one you'll see is the mean, which is another way of saying the average. When you guys have done a numerical average, you've been calculating a mean. So the mean is a measure of central tendency that's obtained by adding up all of the scores and dividing it by the total number of cases. All of you guys have done this before, probably in your own sleep without realizing it, and that's called the mean. Or again, the arithmetic average. It's usually used for interval ratio variables. Again, we can use it for ordinal variables. That's not very common. It's usually interval ratio. And it's the best known and most widely used measure of central tendency, okay? So it is important to note that it is possible for you to get a mean score that's actually not seen in the distribution, right? So it's possible that I give out a test and almost everyone gets 90% or above, and a few people get 70 and below. And so I get a mean that's, let's say, 82.3 when no one got a score in the 80s, right? Why is that?
The outliers balance off.
Right, that's exactly right. So when you use a mean where we're adding up all the numbers, that means you give equal weight to every single frequency, every single occurrence in your data set. So when I get a score that's way out there, it's going to impact my mean because it's being calculated in the same way. Whereas the median is organizing all of them and then picking the middle point. So it eliminates some of the pull from the outliers. So that's one of the reasons, especially for income, that we calculate a median rather than a mean. Because the median is going to be more centered around the middle, the most often occurring number, rather than being pulled by an outlier, right? So especially with salaries and income, you can think there are some people who are making $2-3 million. Well, that's going to pull the number way up when that's not going to be close really to the central theme, or maybe a different way to say that is that number that you get is not going to really tell the most accurate story as to what's going on for income in that population or that community. Does that kind of make sense?
Yep.
Okay. So this is another good example. If the mean and median are both reported, you're going to see again how different they are. So here's salary. This is again the exact example I was using. So this is the percentage of reported salaries. You can see it starts low, right around whatever, $10,000, all the way up to higher than $205,000. And then you see the way it's behaving, right? So you start seeing an increase in percentage. One spike right here, probably around like the 50,000 mark. And then we see a secondary spike maybe around the 60,000 mark. And then it goes down below again. And here we have another huge spike around whatever that is, 150 or 160,000. Which I want to be part of that, whatever that is, right? Okay, so you can see here the difference between the scores. If I were to actually calculate the mean, it'd be 82,408,000. But if I adjust it to account for the fact that we have two separate distributions going on, right? I'm more at a 78,000 or more of a median, right? So this is what's called here, guys, a bimodal distribution, okay? We talked about mode a second again. That's when you're looking at the most frequently occurring number. If we were to split this graph in half right here, we would see that there's one mode right over here at the 150,000, 160,000, and another one right here close to the 50,000. So there's almost two central tendency distribution, or two normal curves within our one graph. So calculating a mean is not as meaningful because all of these numbers are going to drag it out further than it actually needs to be. Okay? All right, so how do we calculate the mean? This is the most common notation. Your book talks about it this way. Just be aware that this is really what we're looking at. So it is the sum of all the raw scores that you have in your data set divided by the number of cases or observations in your data set. So that's your sample size, your N. So it's summing all of the responses, right? All the numbers you saw, dividing it by the number of cases. You've done this 1,000 times, right? You just add it up, divided by the number. So if I were trying to figure out the mean of this data set, I would add up all of those values together. Here it is. That adds up to 60. Then I count the number of cases I have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, divided by 10. And that gives me a mean of 6. Hopefully nothing earth-shattering here. Questions about this?
You good?
Okay. All right. The mean of the distribution is that's the same example that we used before. Remember, the mode was 8. Now I would be adding up all of these, which is exactly what we did right here, right? So the mean is actually 6, right over here. The mode was 8. Let's see, I think I have it again. But we could calculate also the median, which would be taking all of these in order. So it'd be 1, 3, 3, 6, 7, 7, 8, 8, 8, and 9, right? Ordering them and then finding the midpoint for it, which would be a different value as well. Okay. When you are trying to look at the mean of a frequency distribution rather than just a data set, it's going to be a little different. So here's the notations you need to be aware of. When there's a bar on top of your Y or on top of your X, that denotes the mean, right? So it's the mean of Y or it could be the mean of X. Y here is your raw score of the variable, right? The sigma is the sum of all of it. And this is the main change because here we were, whoops, Here it is. You see how this formula is very similar? The only change you're interjecting here is frequency. So you're doing the frequency times that number. So if I were to look here, the frequency is 1. This would be 1 times 1. The frequency here, how many times does this occur? That you get 3 dreams. Is that what it is? Number dream. What's that?
Twice.
Twice. So the frequency is 2. The data point is 3. So I would do 2 times 3. And then I need to add them all up. So let's look at that again, how that would look. So with this particular example. So I am summing the product of the frequency times the number. So this is the frequency, right? 0 all the way through 6. This is the number of children within a family. This is how often it occurs. And this is actually how I'm calculating it. So number of children that happened 8 times, 0 times 8 equals 0. 1 child, it happened 29 times, that would be 29. 2 children, that happened 477 times, 954. And so on and so forth. And then I need to sum it all. So the entire sum is 2,173. But now I need to divide it by n, which is the total number of cases in my data set. And I get that by summing the frequency, which is 862, which gives me an average of 2.52. Now, Kyle, I think that was actually quite close to the number you gave us earlier, so the number of children. Yay! Does that make sense? So you're writing a table, multiplying your y, your data number, times its frequency, and then you have to sum them all up. Once you have that sum, that's what goes up top right here. It's the sum of the product of the frequency times the data point, and you divide it by the number of cases in your data set. Questions about that? It's the same idea as doing a regular mean, except you're using it with a full frequency. Because the truth is, we could do this as a regular mean, but then you would be adding up 862 numbers, right? Which that's a bit tedious. And insert human error, right? Like, oh, I fat fingered the computer or the calculator, and now we start all over again. So instead, you can create a frequency table and just multiply it. So it's meant to be simpler. Okay. Here's another example. So this is the 2014 data on the incarceration rates per 100,000 people for 10 of the most populous states. So here are the states listed. Here's the incarceration rate per 100,000 people. So what would be the average incarceration rate? So you need to first take a peek at, and you also want to look at median incarceration rate. So what is the proportion of people that are in jail in Michigan? So if I were to look, Michigan is 437 per 100,000 people. So I need to divide that up, and we get to 0.437%. For the total US population, again, if I looked at all of that, it'd be 0.7%. So let's do additional math on that one. Oh, maybe I don't have more on that one because that's kind of a funky one. Okay. Let's talk a little bit more about the mean. Few things that we always need to keep in mind. So first, it is always for a measure of interval ratio level of measurement. It is never going to be for nominal or ordinal. It's really interval ratio, meaning it's got to have a value or some sort of measured data or a continuous variable. It's going to have some sort of gravity or center point. So unlike the mode and the median, which incorporates all the scores of the distribution, this one will have like a midpoint, like this is it. This is where it is. It's right in the middle. If you subtract the mean from each score and add the difference, the sum will always be 0 because we are doing a numerical mean. So because of that, it's always going to add up 0. It's just a funky, interesting fact. The thing with the mean, we talked about this already, is it is extremely sensitive to the outliers or to the extremes. So the mean will get pulled in whichever direction where there's high levels of outliers. So if you've got high scores that are kind of pulling out in the middle of nowhere, your mean is going to get dragged up. If you've got random low scores, your mean is going to get dragged down. And as I mentioned earlier, this is why we do not use mean as a calculation for income, because we have folks who make very little money or no money at all, and folks who make a ton of money, right? So that is dragging our mean, which we don't want to do because it loses meaning. Okay, so let's take a peek at the seesaw idea, right? If I've got this being my mean here, this little fulcrum, right? If everything is well divided, it's going to be standing in the middle. But if you could see right here, if I've got outliers towards the top, that's going to push it down. That's going to make everything slide down further. So this is meant to be like a scale, right? Where you're like equalizing it. If it's all average, right? It's evenly distributed, then it's flat. If it tilts one way, which for this instance, it tilts this way, the way to correct it so it's flat again is to move the mean. So this outlier represents a mean increase of about 20 points here. This is a visual representation showing that, the pull of the outlier. This is our example earlier. I think I was mentioning that before. You can see that the mode for this one ends up being 8, right? Because we could see here that's the most frequently occurring number. And the mean is 8.3. So those are fairly similar. Now, if we look here, the mode is still 8, but our mean is over here. Why is our mean so much lower? In the second example.
The values got redistributed lower.
Yeah. So there's more values that are lower. There's a higher amount of them compared to up top, but the highest occurring number is still 8. So the mean gets dragged down, the mode does not change. So again, this is another one. The mode is still 8. Now I've got what's called a bimodal distribution almost, because it's divided into 2, really split. My mean ends up being 7, even though that's not even an occurring number in my sample size, right? There's nothing here under 7, but that's what my numerical mean ends up being. Okay. So it's always important to consider the shape of our distribution. So if I go back here, if you were to do, can you guys see my cursor when I move it?
Yeah.
Okay. So here it would be flat, 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 and then it goes up, which suggests that there's more values on the latter half of my distribution. This one, I'm going up, then going back down and up again, so that there's almost 2 humps. And here there's nothing, 1 hump, nothing, another hump. So really 2 separate distributions. That is important when we're looking at making meaning of our numbers, right? So we always need to consider the shape of our distribution, because it tells us about the measure of central tendency that we should use. In some instances, it makes perfect sense to use a mean, a numerical mean, because everything is normally distributed. But when it's bimodal, right, it's split, there's 2 humps, or it's really skewed, meaning most of the data is on one quadrant, using a mean is not going to be as significant. So that's why it's always important to look at the shape of our distribution. It also helps us when we're starting to do some inferential testing, like imagining or creating hypotheses as to why it's that way. And then it lets us know whether we need to do a data transformation, meaning correcting for a skew or being pushed out on one side. If our distribution is symmetrical, meaning if you cut it in half and it's perfectly symmetrical one side to the other, it means that it's equal to median and mode. It's right there in the middle. The median is all even. That is what's called a normal distribution. If it is skewed, this is the idea that your data is mostly on one part of the distribution or another, so the shape will be different. If it's negatively skewed, your mean is going to be smaller than your median and mode. If it's positively skewed, the mean is going to be greater than your median and mode. Okay, I think I have some pictures here. Let's talk about that in a second. Okay. Something else to note. A unimodal distribution, like the typical bell curve you think of, there's only one mode. It's unimodal. Now, I've showed you guys a few where there's two distinct modes. That's called bimodal. Occasionally, you'll have a super funky distribution that is multimodal, meaning it's got multiple humps, multiple spots where there's distinct modes about the distribution. So let's look at what they look like. Oops, let's move that over here. So this is what's considered a symmetrical distribution. For some reason, this covered up. I don't know why that covered up my writing. So here, the mean, median, and mode are all exactly the same. So again, this is a symmetrical distribution. If I cut it in half and folded it over, it would be identical. This is a negatively skewed distribution, meaning the bulk of my data is where?
The right side?
To the right side, which means the bulk of my data has higher scores, right? If I think about it, because this will always mean the further you go out from the central point, the higher the number, right? It increases. So that means my median is going to be a little smaller than my mode, and my mean falls right here, a little bit below. So that's what we were talking about before. And then here's a positively skewed, little known fact. If you think about it, if the scores there's more scores that are lower, it kind of makes a P. Can you guys see that? If you look at it, more of a P. And that's for positively skewed. Little hint I picked up in graduate school. And you can see how, again, the impact of mode, median, and mean. Okay. Oops. So how do we identify it? Again, this is more discussion as to what I just said. In unimodal distribution, where the mode, the mean, and the median are all the same, it's almost identical, they might be slightly by a point, that is considered symmetrical distribution. So again, if you draw a line down the middle, each side would be a mirror image. When the mean is higher than the median, it's positioned to the right of the median, the distribution is positively skewed. For instance, income, right? And then similarly, when the mean is lower than the median, like, I don't know, this number of fingers, that's a weird example in your text as well. It would then mean that the median is positioned, or the mean is positioned to the left of the median. So again, take a look back at your textbook. These are just examples. I'm not going to ask you to identify which one is positively, negatively. It's just if you think about it, I think it should make some good sense, right? Where the data is higher, it's just going to pull your numbers higher because the extremes are impacted. Okay, why do we care about all that? Why is that even a thing? Part of it is we're trying to figure out when we utilize these measures of central tendency, we need to figure out which one makes the most sense to the example that you're using. So first you need to evaluate what is my level of measurement. So if I'm using a nominal level of measurement like religion type or marital status or state where you live, right? Like, or language that you speak, doing the mode will make the most sense. So it's calculating the most frequently occurring value, whatever that looks like. If you're doing a calculation where the impact of an outlier is going to be significant in explaining away the central tendency, sticking with a median makes a lot more sense, right? If there's any outliers, or if somehow your data is skewed, meaning most people responded in a certain way. I will tell you, my dissertation was on psychopathy, or the idea of, so psychopathy, is that a common, do you guys know what that means? If you think of a psychopath, right? What comes to mind when you think about that?
Serial killers?
Serial killer. That's oftentimes is the most common connection. But there's this idea that psychopathy and being, oftentimes people call them sociopaths, you can actually have those same traits without actually committing crimes. They're called more like white collar crimes, but the traits, the personality traits within that person are going to be very similar to someone who actually acts out and does bad things behaviorally. My dissertation was looking at a particular tool, a survey tool that evaluated the levels of psychopathy in a non-institutionalized, non-incarcerated, so not in a state hospital and not in jail population. And I used it on college students when I did my dissertation. So if you were to take a guess, do you think my data was skewed?
Yes.
Yes. Why is that?
It's only looking at a certain age group and even more specifically a certain age group that's in college.
Okay, so something about maybe my sample or my population did that, but okay, what are other thoughts? Why would my data be skewed on their rates of psychopathy or being a psychopath?
Because you're not looking at the right people, I guess. Because if psychopathy, if you look into like criminals, like that's more frequent. And then the frequency of college kids being, psychopaths or sociopaths, or I think lower.
You would be correct, yes.
Yeah.
So even though that tool was meant to measure psychopathy traits in non-institutionalized, non-incarcerated people, the bulk and the majority of folks responded that no, they did not connect with some of those traits. So their scores were very low, right? So I had lots of people that showed low levels of those traits. Whereas I had a skew, right? Because if I had 4 options in terms of their answers, or even if I looked at the total score, most people scored really low, very few scored higher. So having skew is not necessarily a bad thing. It tells you something about your data, right? So just something else to keep in mind. All right, so this is exactly what I just said. So depending on what it is you're trying to do, what is your research objective, what is your research question, that's going to impact whether you utilize the median or mode and whether you're okay with there being a skewed distribution. If you're looking for a really evenly split distribution, let's say with racial groups, and you've got a huge skew, that might be a problem, right? If you're saying this study applies and I want to generalize it to all people that live in the United States, but you only interviewed like 90% white people, is there a problem with that? That's a pretty big skew. And so then you need to go back to your research question and say, well, did I actually do something wrong? If I want it to be generalizable and I'm saying this is from a diverse group and I didn't actually get that and I got a huge skew, that may be problematic. Okay. All right. So again, this is kind of the decision tree that you would do. First, you start with your level of measurement. What is it? If it's nominal, shoop, you're going straight down to a mode. That's kind of your only option. If you're doing ordinal, it depends on what is your research objective. It could be either the mode or the median. If you have an interval ratio, some sort of continuous variable that you're measuring, look at what the shape of your distribution is. If it's skewed, ask yourself, again, what's my research objective? Do I want the mode or median? If it is symmetrical, it's totally up to you which way you go. They're going to be fairly similar one way or the other. So that's kind of a decision tree to try to figure that out. Okay. Let's get right down to the weird, you guys. Your textbook has lots of fun examples. Okay, this is the responses from 106 men and 160 women to the question, how many partners would you ideally desire in the next 30 years? Here's what women reported, here's what men reported, and here's the median and mode. Looking at this, what are your thoughts?
The men's data is definitely skewed, and I think it's negatively. Wait. Yeah, it's positively skewed towards men for men.
Okay, So what is this, if you're looking at this data, what do you think what would be your take-home message? Anybody else? Kyle's doing a lot of talking. Great participation, Kyle. Go ahead. Yeah, Ada.
Men want to have more partners than women.
Okay, quick take home, right? Now, if I'm just looking at the mean, 100% that, right? In fact, hold the front door, 64. That is not a small number. In 30 years, right? That's more than 2 partners per year. Maybe they mean walking partners. Let's just go with that. Now, if you're just looking at median and mode, what do you think?
There's not much of a difference between women and men.
Right. So what would make the most sense to report?
I guess in terms of similarities or differences, or all of them?
Well, anything you can think of, yeah.
I guess the most significant then would be the mean.
Okay, because it tells more of a story, right?
Yeah.
Okay, any other thoughts?
If you just look at the median and mode, then you could say that men and women want to have the same amount of partners.
Exactly. So if I was doing a study and I'm trying to say there's no gender differences, all people really want to just get married and just live like penguins, whatever the one is, they mate forever, divorce is not a thing, I would probably report the median and mode. If I'm trying to report, if I'm a women's magazine, I'm like, is your guy going to cheat on you? 64% of men actually stated, or no, this is not percentage, but the mean number of partners that men desire in the next 30 is 64, right? Like maybe that would help. So again, this is a prime example of how data can be utilized to support whatever your hypothesis, and depending on what you want to share about it, you're going to share a different number. So going back to my last slide, looking at your research objective is going to have an impact, right? What is your research objective? What is it you want to communicate? You can communicate different central tendency. I bring this up as an example because we'll see that often. You'll hear one data point and then you'll see the conclusion they drew and you're like, wait, but is it? And you go to the original research and you're like, no, that is not the take home. You just took one nugget of it and ran with it, right? Okay. Whoops. Now, this is the exact same thing, right? Let's look at this. So, same exact data. What do we notice now? What do we see?
There's a large group of men in the 11 to 20 partners category, which is probably what made the men's average go up.
Mm-hmm. Yep.
There's a lot of people with just one partner. So
Absolutely.
that would push it down the opposite way.
Mm-hmm. And you can see why the median and the mode ends up being 1 for both, right? That, I mean, it's very clear. Can we talk for a hot minute about these people over here? I don't think that's physically possible. Don't
Very
argue with me on that. This, again, just weird data, but this is the definition of an outlier, right? And in fact, I'm trying to look at it. That's probably 2%. I don't know. What do you guys think? 1 or 2%? Because this is percentage here.
Oh, yeah.
That looks like 1 or 2. Yeah, 1 or 2% of men said 100 to 1,000 or 1,000 to 10,000. I would want to know about reading competency at that point, and I would question whether they understood the question, is all I'm going to say. But, okay, so now if somebody was given this data, it's far more likely that their conclusion would be what? Just eyeballing it, you're asking your grandma, Grandma, what do you think this graph is telling us?
I think it's saying that men and women really aren't that different.
Exactly. I think it speaks volume that the greatest percentage that is seen into the number of partners they want in the next 30 years is 1 for both men and women. And then there's variability, right? On both sides of the gender, variability there, okay? But the main takeaway is this, but if I just did the mean, that wouldn't be as accurate, right? So there's instances where doing the mode or the median is far more meaningful. So I think we tend to always rely on the mean because that's the numerical value. That's when you do the calculation. But don't discount the median and the mode as well. They may be far more appropriate depending on your research question. Okay, questions about this? Does this kind of make sense? Okay, I'm gonna hope for yeah. All right. This is a quick summary. So the mean is the sum of the scores divided by the number of scores. We talked about this again. This is your numerical average. The mode is the value with the greatest frequency within a given distribution. And lastly, the median is the exact middle score when all the scores of a distribution are arranged from lowest to highest. Okay? And when you would use that with equal interval of variables, like we talked about, ratio interval. You would use the mode with nominal variables, and you'd use the median with some sort of rank order variable, especially when you have outliers. This is the most common one. These are some key terms you guys want to keep in mind for this chapter. Here we are. Okay, so it is, ooh, I was so close, 3:27. I was thinking 3:30. All right, so what I'm gonna do is let's go offline right now. I'm gonna add quiz 2 to this week's class. Just like you did last week, you can open it up, write your answers in there, and resubmit it to me. If somehow the submit button, I just want to put a little asterisk to like, there's probably going to be technical issues because this is how life goes. You can always email it to me as well. So let's plan on taking a 10-minute break and then coming back in class at 4 o'clock. Sound like a plan? Because I'm thinking 20 minutes will be plenty of time for you guys to do the quiz.
So 4 is when we start the quiz?
No, great question. Thank you, Elizabeth. You can start the quiz as soon as it's live. I'm going to add it right now. I have to add it right now so you guys can see it and make it visible. I want you guys to each take a 10-minute break, go to the bathroom, do your thing. And then my thinking is you'll go back at 3:40 and start the quiz at 3:40, and we will start lecturing again at 4.
Okay.
Perfect.
Does that make sense? Does that make sense, Elizabeth? Okay. All right. I will see you all back in the Zoom class at 4 o'clock.
See you then.
Okay. See you in a minute.